Hello everyone, my name is Wang. I am a postdoc researcher from Pengqing Laboratory, Shenzhen, China. Today, I will give an introduction to our work towards more flexible and accurate object tracking with natural language algorithms and benchmark, which has been accepted by CVPR 2021 as a poster representation. This paper has cooperated with Xiujun Xu, Zhipeng Zhang, Jiang, Yaowei Wang, Yonghong and Feng Wu. The paper, demo video, dataset, and evaluation toolkit can be found on our project page. For this talk, I will introduce our work from the following 6 perspectives. Firstly, I will talk about what is visual tracking and its issues. Then, I will draw forth the topic we will discuss today, tracking by natural language. I will focus on the dataset collection and annotation for this task. After that, we will introduce our new baseline approach, AdaSwitcher, and report the experimental results based on our new dataset TNL2K. Finally, I will conclude and give some possible research directions on this task. Usually, the standard visual tracking will specify a target object we want to track with a bounding box, like the blue rectangle. Then, the tracker will search the target object in the following video frames with a machine learning model and give a new location to better locate the target object by adjusting its location and scale. This setting is simple and works well in regular tracking scenarios. Many trackers are developed under this setting, and these algorithms are applied in many scenarios, such as UAV tracking, autonomous vehicles, security, and the military field. However, the current setting still has the following disadvantages in practical applications. Specifically speaking, the bounding box is inconvenient to initialize for the first frame. The specified target object may be confusing, for example, the red bounding box is hard to judge which person we need to track. However, previous trackers and benchmark datasets almost ignored this problem. The target object with significant appearance variation is hard to track for the standard trackers. For example, the pedestrian may take his or her cloth off when they feel hot in the street. But current trackers assume the variation of target object between different frames are minute, and they are heavily relying on the appearance model. But the assumption is not valid for this common scenario. Besides, when we want to track the specified target object, it is also not flexible and enough to only use a bounding box. For example, if want to track the player who controls the ball, the player may always change. It is nearly an impossible task for the bounding box-based visual tracking. Last but not least, current trackers also are easily influenced by model drift, local global search, and so on. Inspired by the aforementioned observations, we are inspired to reformulate the tracking task with high-level semantic information to address these issues. Specifically, we formally define the task of tracking by natural language and tracking by bounding box and natural language. With the language information, we can address most of the aforementioned problems in the regular tracking task. For example, the ambiguous significant appearance variation, inflexible, model drift, and global search. The first work in this area is the tracking by natural language specification, which is published on CVPR 2017. However, due to the lack of suitable datasets for this task, they annotate the OTB100 tracking dataset, termed OTB-lang, for their experiments. But the experiments maybe can't reflect the new features of tracking by natural language. Because the videos in the OTB are collected for tracking by bounding box, as we can see from the left list, the recently released large-scale tracking datasets, like the TrackingNet, Xuva, GOT10K, LACET are also specifically designed for bounding box-based tracking. It is worthy to note that the LACET also annotate the language information for each video. However, their language annotations cannot reason the location of the target object in the first frame. Therefore, this dataset can be used for tracking by bounding box and natural language, but not suitable for tracking by language only. Re-annotate the language for LACET is a possible method, but it also can't reflect the significant appearance variation. The videos in GOT10K are all short-term sequences, which cannot reflect the advantage of redetection for tracking task. Therefore, we propose a new dataset, termed TNL2K, which contains 2000 video sequences, and it is large enough for current deep learning methods. It also provides high-quality annotations for each frame, including the bounding box and corresponding natural language information. Our dataset is the first tracking dataset that contains the adversarial samples which can be used for the research on adversarial attack and defense. Our dataset also contains videos with significant appearance variation and heterogeneous data, such as RGB video, thermal video, cartoon, and synthetic data. More importantly, we provide three kinds of baseline methods, including tracking by bounding box, tracking by natural language, tracking by joint bounding box, and language. The comparison between existing datasets and ours are given below. Here, we give some illustrations of our dataset, such as the video frames, language information, and statistical information of video length and challenging factors. There are 17 attributes defined in our dataset as shown in the left table. It is worthy to note that the adversarial sample and modality switch are two new attributes formally proposed in the tracking community. More examples can be found in our demo video on the YouTube website. The link can also be found on our project page. Based on our newly proposed dataset, we construct a simple baseline method as shown in this figure. Generally speaking, our tracker contains three modules: the visual grounding module, the local tracking module, and the adaptive switch module, which is highlighted in blue. Let's talk about each module in detail. The grounding module is used for locating the target object using the language information in the first frame. We use CNN as the backbone to encode the input image and use the pre-trained BERT model to get the language embeddings. Then, the fully connected layers are used to further fine-tune the feature. In addition, we also add the spatial coordinates information to further improve the overall accuracy. These features will be fused with a one-time-one convolutional layer. For the local tracking module, we use the CVPR as the baseline method. To balance the local tracking and global grounding module, we design a novel data switcher model to adaptively switch between local and global search. The language embedding, tracking results, bounding box, and result image are all considered as the input. We also use a BiGRU network to encode the temporal information across different frames for more accurate prediction. Our proposed tracking framework can be used for both tracking by language and tracking by joint language and bounding box. In the experiments, we first test 43 bounding box-based trackers and report the PR, normalized PR, and SR on the TNL2K, respectively. From this figure, we can find that the CVPR, DIMP, and PREDIMP achieve the top 3 ranking. The overall results are still relatively low compared with other tracking benchmarks. For the natural language-related works, we compared with 5 trackers on 3 benchmarks, i.e., the OTB Lang, LACET, and TNL2K. We can find that our method achieves comparable, even better results on these benchmarks. The right figure is the result of our visual grounding module in the first frame. We can find that it works well when the background is simple. We also report the tracking results under all the 17 defined challenging factors. But we also find that the better trackers still occupy a better position under these sub-dataset. The ablation study on the component analysis all demonstrates the effectiveness of each module in our tracker. The right figure is the comparison with other state-of-the-art tracking algorithms. To sum up, we conclude this talk in the following 5 parts. For future works, we will attempt to improve this work from the following 3 points. Firstly, we will introduce audio information for speech-based target object localization. Because some language does not have words, but only speech. Secondly, we will introduce a joint video language feature fusion module for robust representation learning. Thirdly, we will introduce more long-term videos and baseline trackers for future works to compare. Thanks for your attention. If you have any questions about this work, please contact me via wangxiukpr@foxmail.com.